Hello, everyone. I'm Jialai Wang from Tsinghua University. Today, I introduce our work, Aegis, mitigating targeted attacks against deep neural networks. This is our outline, and we first introduce the background. In 2014, the emergence of the hammer attack revealed that attackers could flip bits in memory to achieve malicious attempts. The basic idea behind the attack is to rapidly access specific rows of memory in a way that induces electrical interference, causing bit flips in adjacent rows. By carefully targeting and repeatedly accessing those vulnerable memory locations, attackers can flip specific bits, potentially leading to unauthorized access or privilege escalation. Nowadays, these attacks have advanced to the extent that they can modify almost any desired bit. Building upon such attacks, recent studies have introduced the techniques to modify model parameters. In this work, we focus on mitigating targeted attacks and provide an example of such attacks. The target attack manipulates model parameters by flipping bits of model weights, causing the model to misclassify input X as a target class Y. Although neural networks typically contain millions of parameters, previous work showed that flipping a small number of bits is sufficient for target attacks. For example, as shown in this figure, adversaries can conduct targeted attacks with only 20 bits flipped. Note that these flip bits are carefully selected. Randomly flipped bits typically cannot effectively attack models. That's to say, adversaries need to first determine critical bits with specific algorithms, then flip these bits in real-world devices. We assume that adversaries have the ability to conduct these two steps and present their models here. The attacker's goal is to flip a few bits in memory to maliciously manipulate the model. We assume the attacker knows the model's physical address and the model's weights. Furthermore, he is able to plan his program in memory and start a hammer attack. Note that attackers can flip only a few bits, since flipping a bit is a time-consuming process. To mitigate bit attacks, some defense methods have been proposed. We briefly introduce them and analyze their limitations. Existing defense methods can be categorized into three types. The first two types primarily come from the field of system security, namely correction-based approach and detection-based approach. The third type of defense solution is model network defense. We use such solutions as baselines and compare our approach with them. We first introduced the correction-based approach, ECC, which aims to correct flip bits. ECC works by adding extra bits to data before it's sent from one place to another. These extra bits allow the computer to detect errors and correct them. However, ECC has some main limitations. For example, recent studies reveal that ECC is not an absolutely secure solution against your hammer. Also, ECC is still not used in some devices like DDoS-free in Internet Nano. The second type belongs to detection-based approaches, such as hashtag. They typically use integrity checks, such as signatures, to detect if any bits have been flipped. Although these solutions are lightweight, they do introduce additional computational overhead and extra trustworthy program on shared untrustworthy resources. The third type belongs to model network defense solutions, such as DNN. Such approaches use weight parallelization method to retrain target models, considerably improving model tolerance to bit flips. However, retraining a model from scratch can incur significant computation cost, especially for large-scale DNN models. Also, such methods could hugely degrade model accuracy. After realizing the limitation of existing defense methods, we propose our defense solution, Aegis. Aegis meets three defense requirements. First, non-intrusive. The defense should be easy to deploy on the shared models. The defender does not need to modify model parameters, e.g., retraining a model from scratch, which can incur significant computation cost. Second, we hope to have a platform-independent solution that is generally effective regardless of the underlying software or hardware. Third, utility preserving. A defense should have a negligible impact on model inference. It should preserve model utility without hugely decreasing its prediction accuracy. The key observation behind our Aegis is that we find existing targeted attacks tend to locate the bits first by layer, then parameters. Furthermore, they only flip bits in one layer. For example, some attacks only flip bits in the last layer of target models, as shown in this figure. Other attacks first determine the most critical layer, e.g. the case layer, and flip bits in this layer. Inspired by this, if we break the inference pattern by adopting the multi-exit strategy, namely SDN, to allow samples to exit earlier, we could effectively mitigate such attacks. For example, by forcing most samples to exit early, the flip bits at the last layer will be probably ignored during inference to achieve defense goals. Also, early exit mechanism will not hugely affect the model accuracy, which has been validated by previous work SDN. Based on the analysis, our Aegis adopts SDN to allow samples to exit earlier. Thus, targeting the final or critical middle layer is pointless. However, attackers could observe the exit distribution of SDN and change to locate adaptive critical layer where samples frequently exit. To solve this problem, we propose a dynamic SDN mechanism that randomizes the exit for each inference. Specifically, we randomly mask internal exit to make samples uniformly exit. This mechanism can mitigate the case when attackers flip bits in specific layers, since samples exit in a random layer, which has a low probability of containing flip bits. Moreover, dynamic exit SDN can push the exit distribution to a uniform one, such that there are no critical exits for the adversary to consider. We show the exit distribution of our Aegis and compare with that of SDN in this figure. We can see the distribution of our Aegis is more uniform after adopting the dynamic exit SDN mechanism. With the knowledge of all the model details, all the details of Aegis, the adversary may include all exits to optimize his critical bit search. This will significantly increase the attack cost. That means more bits to flip. Further, we propose robust training to mimic potential bit flip attacks to force the model fit attacks, enhancing the defense effectiveness against bit flip attacks. In particular, assuming the adversary flip bits in the ith layer of model M, it could still possibly affect any internal classifiers after this layer with a certain probability. At the layer output, F underscore IX passes to this internal classifier and affect their predictions. To reduce such impacts, we propose robust training to improve the robustness of the attached internal classifiers, which is shown in this diagram. The key insight of our robust training is to help internal classifiers adapt to the cases when critical bits are flipped in M. In general, without prior knowledge of attacks, we construct a bit flip model by considering only the blind samples inference process to simulate the target compromise model. Then, we craft new samples based on these bit flip models for robust training. These training samples simulate the outputs of flip layers, and internal classifiers will learn such data to correct the prediction from the adversary scenarios. We then evaluate the effectiveness of our Aegis. We evaluate Aegis on 3 white box target attacks and consider both their initial version and their adaptive attacks. We conduct our experiments on 4 widely used datasets with 2 DNN structures. We adopt attack success rate to assess our approach's performance. The lower the attack success rate, the better the result is. Results show that our Aegis could effectively mitigate all attacks from when flipping 50 bits and outperforms all baselines with much lower attack success rate. We further consider flipping more bits. We take CFAR 100 and VGG 16 as an example to evaluate when the number of flip bits increased to up to 500 for all defense methods. Evaluation results are shown in this diagram. Compared with existing defense methods, we observe the text loss rate for Aegis is still limited at a low level for all texts. We also evaluated the additional costs introduced by our Aegis. Specifically, Aegis slightly increased the model size and has a minor impact on the model's accuracy. On the other hand, Aegis also reduced the model's query time, thus improving efficiency. Overall, Aegis is a non-intrusive, platform-independent, and utility-preserving defense methods to mitigate BFA attacks, which make targeted attacks impractical to deploy on real-world devices. That's all. Thank you. Any questions?